I have a theory about who took the last slice of pizza. We use the word like this every day. In common conversation, a theory is just a hunch, a guess based on the gut feeling. Science works differently. It functions as a method for discovering patterns by asking specific questions about how the world behaves and checking the results. When a researcher has an initial idea about how something works, they call it a hypothesis. A hypothesis is a tentative explanation for an observation. It's a starting point that must be able to be tested and proven wrong. Then there is a law. A scientific law is a concise statement, often a formula, that describes a fixed rule in nature. It tells us exactly what will happen every single time under certain conditions. At the top of the ladder is the theory. A theory explains why the laws work. It is a large-scale framework supported by a massive body of evidence, bringing together many different laws and observations into one coherent story. Because theories must stand up to constant testing and evidence, they represent the highest level of certainty in science. When a scientist calls an idea a theory, they are saying it is an explanation that has survived every challenge we've thrown at it. This chart shows the sizes and distances of the planets as they were understood in the mid-1800s. Back then, astronomers were still trying to map the freezing, dark edges of our solar system. They found a problem. The distant planet Uranus was wobbling. It refused to follow the smooth, predictable path that the known laws of physics said it should take. A young English astronomer named John Couch Adams began looking into the math behind this strange movement. At the same time, a French mathematician named Urbain Le Verrier was working on the same mystery thousands of miles away. They both formed the same hypothesis. A massive, undiscovered planet must be hiding further out in the dark, and its gravitational tug was pulling Uranus off its path. This wasn't a random guess. They used the evidence of the wobble to identify a specific gap in our knowledge that needed a testable explanation. Adams and Le Verrier used the established theory of universal gravitation to calculate exactly where this unseen planet had to be. They trusted the framework of the theory to lead them to the truth. They sent their coordinates to telescopes, which pointed at a patch of the night sky where nothing had ever been seen before. Exactly where the math said it would be, they found it. A brand new planet we now call Neptune. As physicist Brian Cox explains, science doesn't require faith because you can verify the results for yourself. You can check that the math actually works. The discovery of Neptune shows the real power of a scientific theory. It acts like a reliable map, allowing us to predict and find hidden parts of our universe long before we can actually see them. Even though Newton's theory successfully found a planet, it wasn't the final word on how everything in the universe moves. In 1915, Albert Einstein introduced a new way of looking at the world. In these papers, Einstein outlined his theory of general relativity. He proposed that gravity isn't just a pull between objects, but a curve in the actual fabric of space and time. Einstein didn't prove the old laws wrong. Apples still fall from trees just like they did for Newton. Instead, general relativity expanded the house of physics, showing us that Newton's rules were just one part of a much larger, more complex system. This highlights the honesty of physics. As Richard Feynman put it, if it disagrees with experiment, it's wrong. New data always carries more weight than old ideas. A theory is strong precisely because it can change. It fits all the evidence we have today, but it stays humble enough to expand when we find better information tomorrow. Carl Sagan noted that the best thing a scientist can do is look at new evidence, realize their old view was mistaken, and change their mind. This image shows cell theory, which explains how every